Well, thank you everyone for joining again. We're going to be talking about a somewhat new red team technique. The reason why I say somewhat is because I don't like saying new because I'm pretty sure that if I think of it, a lot of other people have thought of it. And also, it really isn't a completely new red teaming technique because we've sort of been doing a version of what I will be describing, whether you realize it or not, in like a lot of tools that we've all been using as red teamers and pen testers for quite a while. So this is more of like a spin on an old technique, my spin on an old technique, which I think should be interesting. All right, so this is our agenda for today. We're gonna be covering some key .NET framework concepts. The reason why is because we all have to get on the same page, and to completely understand how this is even possible, we all have to know some key framework concepts. Also, I feel like just talking to pen testers and red teamers out there, there's a lot of a little bit of a confusion regarding some of the .NET framework terms that have been thrown around recently with all the C# tooling coming about. So I feel like it'd be a good refresher for everybody. And just prefacing that I am going to be saying .NET framework assembly and .NET like a lot throughout this webinar, so just bear with me here. After that, we're going to be talking about how to embed interpreter engines and the how to do that, technical details on how to do that. There will be some code, but it won't be that much. And then we're going to be covering some key differences between like BYOI payloads, so bring your own interpreter payloads, versus traditional C# payloads. BYOI, by the way, is a thing that I just came up with. So like, don't be surprised if you haven't heard of that anywhere. And then we're going to be talking about the new SilentTrinity updates. So SilentTrinity is the tool that I've wrote. It's sort of like a post-exploitation tool that tries to weaponize some of the BYOI concepts. It's been around since last DerbyCon, but it was essentially beerware. It was like in a POC stage. So with the new update, it brings it from beerware to alpha, which is sort of a big jump. We're going to be doing a demo, and we're going to be talking about some detection mechanisms, and then we're going to be going with the Q&A. So first things first, we got to understand what is a .NET assembly, because I feel like a lot of people have heard this term been thrown around a lot and not actually understood like what it is. All you really need to know is that a .NET assembly is a blob of precompiled code that any .NET language can interpret and execute. That's a very high level description of what that actually is. And we're not going to be getting into the details of like the .NET assembly format, just because like that's not for the sake of this webcast. That will take way too long. But all you really need to know is that any .NET language can interpret and execute any .NET assembly. Okay. So how do you go about generating a .NET assembly? Well, it's pretty easy actually. So you take any .NET language. So we're going to take C# in this case, and you compile it into an executable using Visual Studio or CSE.exe, which is the built-in compiler for C#. So you compile C# into a.exe, and that .exe is a .NET assembly. Okay. Here is where things get a little bit interesting, because if you compile C# into a DLL, that DLL is also a .NET assembly. So from the .NET framework's perspective, the .exe and the .dll are the same exact thing, because they're both have been compiled from a .NET language, which in this case is C#. So that's a key distinction. A really important concept to understand is that .NET assemblies are not the same as native XEs and DLLs. So by native XEs and DLLs, I mean executables and DLLs compiled using C or C++. Okay, the format is completely different. So just because they have the .exe extension, they're not the same thing. So if you compile a .NET language into an assembly, that's going to be a completely different format as a native XE and DLL. Okay, so that's just a thing to get out of the way. So as I said earlier, like an assembly is something that any .NET language can interpret and execute. So let's take a look at some of the .NET languages here. So we got PowerShell, we got C#, and we got F#. So these are like the three officially supported Microsoft .NET languages that I'm aware of, at least. There might be others that I might have missed. These are the ones that I know of. So these are all .NET languages. What's really interesting is that there are other .NET language, third-party .NET languages as well, such as IronPython. IronPython is just a Python implementation, the implementation of the Python programming language on top of the .NET framework. Okay. There's also Boolang, which is somewhat of a lesser-known third-party .NET language, but it's very, very interesting from an offensive tradecraft perspective, and we'll be talking about that later. And there's also IronRuby. So like if you want to write Ruby while accessing the entire .NET API, you can totally do that. The key thing to understand here is that all of these languages are built on the same exact framework. They're built on the .NET framework, okay? So what that means is that because of that, these languages are completely interoperable with each other. So you can embed C# into Python, Python into C#, or rather, sorry, PowerShell into C# into PowerShell, and it'll just work because they're all based on the .NET framework, okay? And they're all bound together by the single unit of execution, which is the .NET assembly, okay? So that's just the important thing to understand here, is that these languages are completely interoperable with each other. So now that we understand that, let's talk about the reason why C# tradecraft has been all the rage recently, okay? And I think this is another core concept to understand when it comes to C# tradecraft, because it all really, the root of why it's so appealing for red teamers and pen testers is because of this single function called assembly.load, okay? Assembly.load is magical because it accepts, among many other things, as the first argument, a byte array. So the implication of that is that you can just feed it raw bytes of a .NET assembly, okay? And it will take those raw bytes, load that .NET assembly in memory, and now you have full access to all of the code that you've defined in your .NET assembly. And remember, like, how do you generate a .NET assembly? You generate that by compiling any .NET language. The de facto one is C#, okay? So this is really at the core root at why this like C# is really, or really any .NET language, really is appealing from a tradecraft perspective, because this one single function really is, when you go to think about it, the equivalent of having reflective DLL injection and reflective PE injection built into a language and into a single function. Because as we talked about previously, like a C# DLL is a .NET assembly.
Hey, Marcelo, quick question.
Yeah.
A comment, not much of a dev. Does that essentially mean you can write PowerShell, pepper it with Ruby and Python, then compile it into a .NET compatible exe and it will just work?
Okay, wait, run that by me again. PowerShell.
Says, does that essentially mean you can write PowerShell, pepper
Okay.
it with Ruby and Python, then compile it into a .NET compatible exe and it will just work?
Yes. So incredibly enough, yes. That's exactly what we're going to be talking about later on. Only we're not going to be using Ruby, but we're going to be IronRuby. So it's important, again, like the distinction here is you would have to use IronRuby, obviously, not the original implementation of Ruby. I think, at least, the original implementation of Ruby is based on C. So that's not a .NET language. IronRuby is based on the .NET framework. So yes, as long as it's a .NET language, they're completely interoperable with each other. And this is exactly what this webinar is going to be about, and we're going to be talking about a little bit of that later, only with IronPython as opposed to Ruby. Are there any other Jason? Are there any other questions before I go on? By the way,
just one more. I think it is, so flood the memory space byte array with a NOP sled, then followed by the payloads. I think they're trying to figure out how this works.
No, you literally just give assembly. So the assembly.load function just accepts a byte array. So you can literally just give it the raw bytes of a .NET assembly, right? So you compile C# into a .exe. You can just read the raw bytes of that .exe and feed it into assembly.load, and it'll work.
Gotcha. I think we're good. Move on.
Okay, sweet. So this is really at the root of why C# tradecraft is so appealing, because this assembly.load function is built into the language, okay? And so I keep saying C#, but just keep in mind any .NET language has the assembly.load function, okay? But it's basically reflective DLL, reflective PE injection, built natively supported by a programming language, okay? And there are a lot of implications to that. One of them is that this allows embedding interpreters and engines within other .NET languages. And incredibly enough, you've probably all done this at least once or twice using a tool that a lot of pen testing and red teaming tools in a certain way or fashion. So the de facto example of this is using something like Powerline, or something like NPS, for example, not PowerShell. So Powerline is just a C# executable, okay, that embeds a PowerShell run space. So it's embedding the PowerShell runtime inside of the C# executable, okay? And the reason why it does this is to bypass people who have locked down PowerShell.exe. So Powerline is basically meant to run PowerShell without PowerShell.exe, okay? And the reason why you can do this is because PowerShell and C# are both .NET languages. So they're completely interoperable, which means you can totally embed just the actual PowerShell interpreter, runtime, or whatever you want to call it. I guess run space is the actual term, in a C# binary and just execute PowerShell code. You can even do the reverse. And you've done this a lot too in a lot of PowerShell, offensive PowerShell scripts. A lot of offensive PowerShell scripts do this in order to access native methods, with the exception of like the PowerSplit stuff, which uses like a whole different thing. But you can embed C# code in a PowerShell script. So like the example on the right here, so that's just literally copy and pasted a C# class into a PowerShell script, and then all you do is call this add type function. Now this add type function goes out, calls csc.exe, which is the built-in C# compiler, which is installed by default on every Windows machine, dynamically compiles that C# code, calls assembly.load in the backend to load it into your current PowerShell runtime, and now you have just magically, that all happens at the backend. After that, you just have magically access to all of the functions that you defined in your C# code. And this is mainly used to call native methods, and by native methods I mean like low-level 132 API calls that usually are needed to like inject shellcode and that kind of stuff. So you've been doing this in one way or another already. Like this is not something new. But the thing is this, right? There are more than just PowerShell and C# language. Like the PowerShell and C# are not the only .NET languages, right? There's F#, there's IronPython, there's a bunch of third-party .NET languages that we can do the same thing with, okay? And from a red team tradecraft perspective, the advantages of doing that are enormous, because as of right now, all of the defenses that are in place for PowerShell are confined to the PowerShell runtime, okay? They're not built into the .NET framework itself. They're not built into the underlying framework. So that means that all you have to do to get around all of PowerShell's defenses, so AMSI, script block logging, transcription logging, module logging, constrained language mode, all of those go away immediately the minute you switch to a different .NET language. So C#, for example, and that's why we're seeing this huge tooling migration towards C# right now, because C# is by far like the most similar language to PowerShell. And hell, you even needed to know C# somewhat to do certain things in PowerShell. So like it was just like the most logical jump, right? But it's not only PowerShell. Like you can use IronPython, and because these are completely interoperable with each other, you can embed IronPython in PowerShell. You can embed PowerShell in IronPython. You can embed C# into IronRuby. You can embed IronRuby into Boolang. Like all of these are interoperable with each other because they're based on the same framework, okay? So the problems, okay, well, before I jump into that, actually, so the main reason why you'd want to actually do that, though, is because C# is a compiled language as opposed to IronPython, which is a scripting language. And we'll talk about and from an operational red team perspective, like that is sort of a big deal. So you can use the IronPython scripting language natively on Windows by embedding it in a C# binary, okay? And we're going to be talking about how to actually do that now. And this is really at the core of what SilentTrinity does. This is the core concept that SilentTrinity uses, okay?
So, Marcel, a quick question.
Yeah, sure.
Can you nest these indefinitely, such as embed IronPython into IronRuby, into Boolang, into PowerShell?
Absolutely. This is the fun part. It's called I've called it engine inception. You can nest multiple engines within each other. Hell, in IronPython's case, it's even great. It's even great. Like I think IronPython has like the best implementation of this because you can literally embed infinite amount of engines within each other if you wanted to, for some reason. Like I'm not sure why that's a thing, but you can embed an IronPython engine within an IronPython engine within a C# binary within like a PowerShell script if you wanted to. And that's incredibly enough, that's how the PowerShell stager for the new SilentTrinity update works. So yeah, you can totally embed multiple engines within each other.
I think you're blowing a bunch of minds right now. Does the
Yeah.
target does the target need to have Python binaries to run, or does the embedding take care of those dependencies?
So we're going to actually talk about that right now. So the embedding straight out of the box, if you didn't pull any trickery with assembly loading and stuff, yes, you need to install. So again, and just the key distinction here, this is not normal Python. This is IronPython, okay? Because Python is based off of CPython, which is based in C. So that's completely different language. IronPython is based on .NET, right? But natively, so you can't run native IronPython scripts on Windows because when you embed the engine, it requires 4 DLLs that are not present on Windows by default, okay? So, and these are the DLLs. So there's IronPython.dll, there's IronPython.modules.dll, Microsoft Dynamic, Microsoft Scripting. If I recall correctly, those two Microsoft DLLs are signed. Don't quote me on that. But actually I have not checked that, which is kind of dumb of me, but I'm pretty sure those are signed. The IronPython and IronPython module DLL are not. So when you embed an engine within IronPython engine, at least within a C# binary, these 4 DLLs are required. Okay. So how do you get those DLLs to run? Like how do you get them on the target system, right? There are a number of ways. Like you can, I mean, from an operational perspective, like it wouldn't be great if to call like your target up and just say, hey, can you install IronPython for me so I can like run my malwares, right? So we need to figure out a way to run IronPython natively without the actual installation process. Well, these 4 DLLs are the only thing that are actually required in order to spin up an IronPython engine within a C# binary. Okay, so traditionally, the way you did this in any really .NET is in C# specifically is use something called ILMerge. ILMerge, really high level, just takes all the assemblies that your C# executable needs to run and just merges them within that a single binary itself, okay? And does some like hooking stuff so that when the C# binary actually runs, it automatically just loads them from the binary resources, okay? But the problem with ILMerge is that it actually is really hacky and it doesn't handle a bunch of edge cases, and it also it doesn't handle at all support for dynamic languages. And by dynamic languages I mean like scripting, .NET scripting languages such as like F# and IronPython. So ILMerge is out of the question. What's great about C# though, and this is I forget his name, Andrew Richter. I'll look it up later. But there was this one guy who wrote a C# book and posted this on an MSDN blog, this technique on an MSDN blog. Turns out in C#, and again, like these APIs, these are just .NET APIs. So when I say C#, it's the same thing in like F# or PowerShell or IronPython. There's this one hook. It's called the assembly resolve hook. Okay, and this function gets called every time .NET fails to resolve an assembly. Okay, so when you run your C# executable with an embedded IronPython engine, it's going to try to call assembly.load on those 4 DLLs automatically because they're just a required dependency, right? Well, the problem is if they're not installed in the GAC, which is basically like the equivalent of like the path on Nick system, where like all of your .NET assemblies, all of the default .NET assemblies are in the global assembly cache, which is called the GAC. The C# will call the assembly.resolve function every time it fails to load an assembly. So what we can do is we can actually hook this function and add our custom logic into it. So whenever C# fails to resolve an assembly, it will call this function. And this gives us an incredible amount of flexibility because you can just throw your logic in this one function and you can just and return an assembly.load and just call assembly.load once you actually pull down the DLLs, and automatically C# will just load the assemblies for you. And this is exactly what SilentTrinity does. So SilentTrinity has some logic in this myResolve event handler function, which is basically just a hook on the assembly resolve method that downloads a zip file, an encrypted zip file. Now that's part of the new update, which we'll talk about later. Automatically unzips it, sees if the requested assembly is in the zip file, and just loads it dynamically into memory. Okay, so whenever the SilentTrinity C# stager fails to resolve an assembly, it will download it directly from the server, because we can put any, and that's just like one possibility, right? Because you can put any custom logic in this one event handler, which is fantastic. And then after that, all you really need to do is just call python.createEngine. Python is a type of the IronPython.hosting namespace. So python.createEngine that embeds a Python engine, and then you just call engine.execute, and that will just literally run Python code. So in this case, I'm just printing what to the screen. So that's literally all you need to do, which is fantastic at a really high level. Once you do that, you can just throw Python scripts at that engine, and it'll just execute them. So this is taken from like the message box module in SilentTrinity. It's literally like 7 lines of Python. Like it's probably going to be like 4 if you get rid of the spaces. But you're just calling you're just importing the CLR module, which is IronPython's way of referencing assemblies. Okay, so you do CLR.addReference system Windows Forms, which references the Windows Forms assembly. You just import the class that you need from that namespace, and then you just call message box on it. So you're dynamically executing .NET assemblies from dynamically executing .NET APIs from an embedded IronPython engine within a C# binary, which is pretty legit, I think. Yeah, go ahead.
So we got a couple of people who are asking, wouldn't requirement of additional DLLs that are not native permit the red team to just monitor for those DLLs and just negate execution?
Yeah, so the thing is this, that's sort of the problem that we're facing right now, because there are no optics. There's not a good way of determining which assemblies, like you can, okay, so there's not a good way of detecting specific assemblies that are getting loaded reflectively, okay? So you can do it. You can detect it using event tracing, and we'll talk about this during the detection phase of this webinar, but you can do it using something called ETW, which is event tracing for Windows. The problem with that is there really isn't I don't think there is a tool right now that allows you to capture this information at scale. So in an organization, like you just won't be able to do it. And the reason why you can't detect these assemblies being loaded is because there aren't any optics into the .NET framework right now. Because like let's go back to this chart. Remember, like we're now like way beyond PowerShell. Like we're just a layer. We're just in a completely different dimension than PowerShell. We're actually talking directly to the .NET framework from a third-party language that doesn't have any of those defenses built in. So there are no optics in place for that right now. So we're just completely bypassing PowerShell, all of the PowerShell defenses, with a third-party language, because all of those defenses are built into the PowerShell runtime as opposed to the underlying framework, if that makes sense.
Yeah, I think we're good. You can move on.
Okay, sweet. So at this point, we've embedded an IronPython engine. We've solved the problem of natively executing IronPython scripts on a Windows machine and dynamically resolving assemblies. So we can just throw IronPython scripts at this one C# binary, and it'll just dynamically execute them and dynamically call net APIs. So from here, like this is just a really dumb example, but you can do anything that PowerShell can do using IronPython, and with a couple of exceptions, which we'll talk about in a minute. But I found a way around those exceptions, so that's fine. So now let's get into talk about the difference between BYOI payloads and versus traditional C# payloads, and pros and cons for each, right? So C# payloads, C# is always pretty straightforward. Like it's just straightforward. It works against all .NET versions. But the problem operationally is that there's a lot of compiling all the time. Like you just have to compile the state, you have to compile all your modules, like you just have to compile everything all the time. And there's also like a pretty big overhead in terms of setting up a development environment because of Visual Studio and all that stuff. So like operationally, it isn't the best, right? It's not a scripting language. And you also have to worry about the .NET version for everything because you have to compile your C# against a specific .NET version if your target has like a less than 4.0 version of .NET installed. So there's all these things to take into consideration. As opposed to BYOI payloads, right? So because we're interfacing with .NET through a scripting language now, this means that number one, from an operator's perspective, from like a pen tester's perspective, you can now build your modules in a scripting language of your choice as opposed to C#, right? So you're using all the power of Python or the power of Ruby or the power of Boolang to build your modules that just interact with the .NET API, which is a major advantage because like this, you don't necessarily have to learn C# now because like you just build your modules that inject shellcode through the .NET with Python. And you can take advantage of all of Python's string interpolation stuff that's a little bit more straightforward than C#. So like it's just easier to use this way. You don't have to compile stuff. The most that you have to compile things is once for the C# stager. So everything after that is dynamically executed. So you don't have to keep compiling your assemblies all the time. It also allows for quick retooling and weaponization because, again, it's a scripting language, right? So if you just, if you come across something that you've never encountered before and you need to write a module on the fly, it's Python, like, or Ruby, or whatever language you choose to embed. So like it's just more efficient. So from a operational perspective, I think it's just more efficient. And we already talked about this because the concept of engine inception, right? You can embed multiple languages within each other, multiple interpreter languages within each other. So not only are you creating insane amounts of reflection all the time, which is really hard to detect all of this embedding going on, but it also allows an incredible amount of flexibility in terms of module creation and payload execution because like you can say you wrote a module, like someone wrote a module in Ruby, you can just embed the Ruby interpreter within your C# payload and now you can just run that. Like so and then a friend of yours wrote like a Boolang module, you can just run the Boolang module. It's fine. Like whatever language you choose to embed, like you can execute. And there's also the fact that there's ephemeral code / modules. So what I mean by that is when you execute Python code through an embedded interpreter, from my understanding, my current understanding of this, which might change, and from the code that I've seen, is that after the actual Python gets executed, it gets garbage collected, which means that the Python code that you're executing should not be even in memory. Like it only executes in memory, and after it finishes executing, it just disappears. So if you went to actually perform live memory forensics on a incident where something like this was running on, and you didn't capture the memory at the exact same time as the module was executing, that your malicious code was executing, I'm pretty sure you will not even find it in memory. So it's like this whole, it's a whole different ballgame. There are some downsides to using BYOI payloads though. The main downside as of right now is that it usually will not work on .NET less than 4.0. And the reason why is because there's certain keywords, like there's dynamic keyword that was introduced in .NET 4.0 that allows all of this stuff to work. However, I think I have figured out a way to get around that, but it will require a decent amount of time and effort. So, but as of right now, none of this, like SilentTrinity won't work on machines that have a .NET version installed less than 4.0. But my argument for that is that the reason why you'd want to use SilentTrinity in the first place is to interact with .NET without PowerShell, right? So because of that, if you're on a machine with .NET like 3 installed or 2 installed, you can just revert back to using PowerShell scripts. So like in my mind, there really isn't that really isn't a a con per se, because you could just use the old PowerShell tooling if you come across a machine that has .NET 2.0 installed, for example. So, and this brings us to SilentTrinity, and this is the tool that I've been talking about, I've been developing for quite a while now, and it sort of tries to weaponize a lot of these concepts. And we're going to be talking, and let's really quickly, I'm going to be demoing this in a second. We're going to be, let's really quickly talk about like some of the updates. So it went from 0 to 1, that's 0.1.0. So we're out of the beerware stage, we're out of the proof of concept stage, and we're into alpha, which is a good thing. A lot of big updates. So the first one is that the comms between the C# stager and the server are completely encrypted using elliptic curve Diffie-Hellman key exchange, which is a hell of a mouthful, AES-256 and HVAC. So it uses public key cryptography, and everything's completely encrypted, including the staging. So the actual zip file with the DLLs that it gets sent down to the client, that's all encrypted. It also now integrates Boolang support. So you can now create Boolang payloads, send it down, and those will get executed as well. And I'll be talking about Boolang a little bit in a second. The CLI tab completes everything, which is fantastic. So previously it did sort of tab complete a lot, but the actual GUIDs of the sessions that you got are very long and did not tab complete that, and that was like really annoying. So everything's tab completed now. You can now customize the check-in interval of the sessions using the sleep command, which is always good. And there's now a help menu function, which that also comes in handy. So Boolang support. The reason why Boolang is interesting. So IronPython has this embedding IronPython within C# has this one key deficit, which is that you can't access native methods directly. The reason for that is because in order to import functions in native DLLs, which you can do in C#, it needs a third-party module, not a third-party module, rather, a module in IronPython standard library. When you embed the IronPython engine, it does not have access to the standard library anymore, which is fine because you could just use .NET to accomplish everything that you needed to do. So it's fine. But the problem is that one CLR module, it was required in order to access native methods. So to call like all the functions that injected shellcode, for example, to call all the low-level functions to do like crazy stuff that we could do, like inject mimikatz and all that stuff, you needed to access native methods in order to do that. And you couldn't in IronPython. So Boolang, on the other hand, is very interesting. Number one, at least for me. And number one is because it's extremely inspired by Python. So the syntax is almost completely the same, but it also has native support for importing native functions using just like you would in C# the DLL import attribute. So you can just decorate a function with DLL import, as you see here. In this case, we're calling the mini dump write dump API, which allows us to take a memory dump of a specific process. And we're dumping LSASS. So we can now, through Boolang, have access to native methods, which is fantastic because this allows us to go as high as we want, as low as we want, and to do all the crazy stuff that we usually need to do during red teams, like inject shellcode. Another really cool thing about Boolang is that so when you compile, usually the way you compile, we did this through PowerShell, was through that add type function that I talked about previously. The problem with that, from a tradecraft standpoint, calling add type is not ideal because it leaves artifacts on disk. Because when you compile C# code through PowerShell, it uses cac.exe and it leaves temporary assemblies to disk. So the advantage of using Boolang for this is that everything is in memory. Like nothing touches disk. The way it does this is through IL code, so intermediate language code, which we won't get into. But it dynamically creates an assembly and then executes an assembly directly just directly in memory. So nothing touches disk, and you have access to native APIs. Demo. Okay, let's all start praying to the demo gods now. The first thing I'm going to do is start up SilentTrinity. So all you do is type Python. You download the repo, you install it, python.st.py, and it dumps you into the menu. So if you've used Empire or Metasploit before, you'll feel at home here. It also has the concept of resource files. So like in Metasploit, where you can give it a resource file, which will like automate sending commands to the CLI, you can do that too. So in this case, I'm going to give it a resource file, which just automatically starts an HTTPS listener for us. Okay. And before I like execute anything, I just want to point out like I love the way I built the UI in this thing, so I'm just really excited to show this off. So like the autocomplete function in this is pretty cool. Like it shows like all of the, if you press tab, it gives you like a little menu thing that you can choose your command from. It also has the help command now, so if you're more into using the traditional style of things, that's great. So once you have this all set up, you now need to generate a stager. So you go into stagers. So now you list the available stagers. Right now, in the new update, this is the new update. So there's PowerShell, there's Wimic, and MSBuild. So PowerShell, pretty straightforward. Wimic uses the XSL command execution method discovered by subT. The thing about that is that Defender will just block that. So it's there just for like posterity's sake. It's there just so like you can test in your environment that actually does get blocked. My favorite though is MSBuild, and we'll be using that for a second. So it's really easy. Just use MSBuild. There aren't any options for the MSBuild stager yet, so you just generate it. The way you generate it is that you just hit generate, and then you give the listener name. So up here, we started a listener called HTTPS. Pretty straightforward. So you just generate HTTPS, right? So that will now generate to disk on wherever the server is at, a MSBuild file with an inline C# task that will embed an IronPython engine and do all the stuff that's needed to get us a SilentTrinity stager. So I just copied that over here already. So this is our MSBuild stager here. I'm going to open up a PowerShell window. And thankfully, the server gives us a handy dandy command to in order to get this running. So you literally just have to copy and paste this into the window here. And there you go. So that already did everything. So what it did, let's break this down. So first thing it does, it does an HTTP post request to the endpoint on the server, in which does the public key exchange. Okay, so it does the key exchange. It then generates a shared key, and then once we did that, it downloads the encrypted zip file. So it got downloaded 1.9 megabytes, which is the zip file containing the assemblies. Then it embedded the IronPython engine. C# automatically resolved all of the necessary assemblies inside of the zip file. So you see here, found IronPython DLL and zip, found and main.py.zip. So main.py is in the zip file as well, and that is the main logic of the payload, if that makes sense. So the actual logic for the session, the actual stage logic really isn't in the C# assembly itself. It's just Python code that gets dynamically loaded. So the implications of that is that if you now try to decompile this C# stager, so like the C# stager of SilentTrinity on this, the only thing you'd really see is just a URL and some HTTP calls being made to the URL. You wouldn't be able to look at the logic itself because it's only in memory and it's being executed dynamically through the IronPython engine. Okay. So once it did that, it also loaded the Boolang interpreter DLLs, which are needed to get Boolang executing. And once we have that, you see here that sent the stage on the server side. Now we have a session. So let's go over to sessions. This is going to look awful because the font is insanely large. But so we got the GUID here, and we got the user. We can type info, and this is the great part because now everything's auto-completed. So the GUID, you don't have to type that out, thankfully, or copy and paste that. We got some just general information about the system that we just compromised. And now the fun stuff, right? So we get over to modules. We list out the modules. So now, if you used SilentTrinity before, you'll see that it's a little bit different here because you got the IronPython modules, and then you got the Boolang modules. So you have a choice of and both of them have pros and cons, which we talked about. Like you can't really call native methods with the IronPython modules, so you kind of have to use the Boolang modules for that. But just to give you a demonstration real quick, I'm going to use the the IronPython message box module, okay? The options, you get the title and the text, just as it's just going to pop a message box, and then you run it on the endpoint, which will result in, I'm assuming that's it. Yeah, there you go. So there you go. There's the message box. What's great about this is that you can take advantage. This isn't normal Python. This is IronPython, which is based on .NET. So you can take advantage of .NET's tasking and threading to actually make this agent asynchronous. So if you like just stack up a bunch of modules to run here, you'll see that it'll just keep popping message box because it's the agent itself is fully asynchronous. So while it's executing other modules, it keeps calling back for more jobs, if that makes sense.
Quick question.
Yeah.
And this bypasses an up-to-date MS Defender install?
Yep. And we're going to be going into a Mimikatz module straight after this. So I guess I can show you I'm not cheating here.
And a lot of people were loving this. And one guy said, or Jim said, ooh, so many ideas how to screw with Defer.
Yeah. So yeah, hopefully like part of this webinar was to convey this in a little bit more understanding way, because I think I did a really bad job at my DerbyCon talk. I didn't really fully like explain well how this actually works. Just to give you an idea, so real-time protection, cloud delivery protection is on. The only thing that's turned off is automatic sample submission because I don't want Microsoft, getting my malwares. So let me pop this. So it's going to be fun looking at the server now after you pop all those, because you'll see that they all returned results as the thread exited. So it's completely asynchronous, which is fantastic.
I got one more question.
Yeah.
This has come up a few times. Have you tried this against a .NET 4.8 early preview that has built-in anti-malware methods?
Yeah, I have not yet, but I know a friend who's sort of been doing the initial research on it, and apparently it's not really as fleshed out as it should be. So what I'm gonna do is I'm gonna wait until that's actually like completely stable, and I'm gonna test it out against it and see what happens, because I feel like if I do that now, it's not fair, because I think the release is still in beta, so it's not even completed yet.
One other comment is someone's going to use it today. They've got an EDR to test. That's awesome.
Yes, definitely. Let me know. I've tested this against a couple of them. My recommendation to testing this against EDRs is to use the MS build stager, because if you use the PowerShell stager, it's sort of the PowerShell stuff is only there for convenience. Like, it's sort of defeating the purpose of using PowerShell if you use this tool. So, and speaking of that, we're going to jump right into a Mimikatz module. Okay, so we got the IronPython Mimikatz module here. Okay, so it runs the standard privilege debug, secure LSA, yada, 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 log on passwords, not in high integrity. All right, wait, let me start a administrator PowerShell session so I can run Mimikatz. Okay, let me just copy and paste this. So now we're gonna get a session running as local admin. Okay, so we got a new session here. And just before I do that, so like Empire, if it's in a high integrity process, the session will have like a little asterisk in front of the user. So that's just a quick way of doing it. So let's try to run this on the new session now. There you go. We've run Mimikatz. So breaking this down, okay? We're using C#, inline C# task within an MS build file that embeds an IronPython engine that executes Python code, which then embeds another IronPython engine that executes the actual module that we send down, okay? So let's talk about, so I think that's pretty cool. And there's like a bunch of other modules as well. I'm gonna show you the mouse shaker one, because that's just funny. So we get, this is a Boolang payload now. Did I do that on the right thing? Yeah, there you go. So you can see that my mouse is now going crazy. So that's a Boolang payload that executes Boolang interactively on the fly. And there's a bunch of others. Like, I could probably be here all day. Execute assembly. If you're familiar with like the Cobalt Strike execute assembly command, that's exactly what it does. It takes a C# executable and just executes it in memory. And again, the reason why we can do this is because these languages are completely interoperable with each other, right? There's an internal monologue. Let's talk about detection for a minute. So what's really interesting, actually, this is MS build. So, all right, let's see. Let's open up Process Explorer real quick. There you go. So, properties. Does it have, yes. Oh, and damn it. Okay, wait 1 second. Let me start this as administrator rights. So Process Explorer, for those of you who don't know, Process Explorer can view loaded app domains and assemblies that are being used in .NET processes. So if you just go over here to the MS build task that we spun up, you'll see that the .NET CLR is loaded, right? And this is sort of the main problem that I'm going to tackle now. Well, not now, but like after I get done with this webinar. But so you can see here that in the app domain, we have the IronPython assemblies loaded and the Boolang assemblies loaded, which itself really isn't a IOC per se. But the thing is, they're not image backed, right? So these, you can see, because all of these other assemblies have an image backing. So they have an assembly on disk. These don't. The reason why is because they were dynamically loaded, right? So that's one possible IOC, right? Another IOC is obviously the name SilentTrinity, which, okay, that's a dead giveaway. But PE loader. So this PE loader right here is actually a modified version of Sharpsploit's portable executable loader, which is what's used in the Mimikatz module to load Mimikatz, right? So it's a C# PE loader. So if you're using just the standard Sharpsploit library, you would see that that would be Sharpsploit in there. So that's another potential IOC. So the current problem right now with SilentTrinity is that it loads everything in a single app domain. So if you went to actually inspect the process and you actually went to dump all the assemblies that are loaded, you will see that like a bunch of known malicious C# libraries and assemblies are loaded, right? I have figured out a way around that because apparently you can embed IronPython engines within a different app domain. So what that means is that, and this is something that I actually wanted to get working for this webinar, but I just didn't have enough time to figure out some of the bugs that I encountered. But what that means is that you can spin up a separate app domain for each executed module. So when the Mimikatz module executes, for example, it will be in a separate app domain, and then after it executes, the app domain will get unloaded. So when you actually go to inspect the process, you won't see the Sharpsploit module loaded unless you grab it right when it's executing, which is almost impossible because it takes like only like a second to execute. So you can totally do that. And I am like almost 95% there. I just need a little bit more time to figure all the bugs out. So this is one potential IOC, which you can detect using Process Explorer or something. The problem is at scale, this doesn't really work that well. And we're going to talk about that in a second. So let's go into detection.
Is the SilentTrinity in the task manager part of the de-weaponization?
I'm not exactly sure what that means, but I'm going to assume he means if you can see it in the task manager. If not, I mean, so depending on how you execute the stager, you could, like if you just run the SilentTrinity C# binary, you'll obviously see the C# process, the SilentTrinity process. But the thing is, like, you can embed it in PowerShell, you can embed it in MS Build because like this stuff executes C#. So you'd only be able to see like msbuild.exe or PowerShell.exe, if that makes sense.
And then app whitelisting has been coming up a lot. So have you found app whitelisting like Bit9 capable of blocking this attack, ignoring the implications of EDR detection?
Yeah, so I have tested this against a number of EDRs. The thing is, when whitelisting is involved, I mean, like any other, I'm gonna go back to the VM here. Like any other like binary, like this is the SilentTrinity C# stager, like that's just a C# assembly, right? This is the MS build stager. So in order to get around whitelisting, you just have to use like a known whitelisting bypass, which is why MS build is built into SilentTrinity. The MS build stager that I just showed you here, that's a whitelisting bypass. So I know it actually does get detected on this thing does get detected on like a couple of hours, but this is just a straight up whitelisting bypass. There really isn't, because there are no optics in .NET right now, there really isn't a way for EDRs to hook into the .NET framework, the underlying .NET framework, in order to actually detect this stuff. And this is where like this detection slide comes in, because so .NET 4.8, as it was brought up, like has AMC integration already. Now I'm gonna wait until it's just fully stable and then test SilentTrinity, because like the beta I feel like would give me like false confidence and stuff. So I'm gonna wait until that's done. There has also been a lot of awesome like proof of concept detection mechanisms being done by Manifestation and Ryan Cobb's of SpecterOps. So Manifestation came out with the collect.NET events PowerShell script that hooks into ETW, which is basically a low-level logging mechanism of Windows. That's probably like the most high-level way of describing it. And you can actually enumerate assemblies being loaded in real time by hooking ETW. The problem with this is there really isn't a tool to do this at scale. So like for enterprise stuff, like it's not feasible to do this. So we have to wait until Microsoft implements optics into .NET in order for like security EDR solutions to actually support detecting this kind of stuff. Crab's ETW is basically a C++ wrapper on for ETW, as the name implies. So potentially you could like write a tool for your organization that does this in C++, but like, yeah, that probably is going to take a decent amount of effort. There's also a really good talk by Luke Jennings on Blue Hat 18, which talks about mesy-to-resident implants and it talks about some of what I just described and some detection mechanisms as well. And I think he wrote a Python script that hooks into ETW as well. So there's that. Countercept, which I think is an MWR company, I might be wrong, but quote me on that, did a really cool blog post on hunting for SilentTrinity, which actually has some of the detection mechanisms that I just told you. And also Ryan Cobb's, big shout out to him because he put together the Sharpsploit library, which is what allows the Mimikatz thing to run currently. And he put together a nice blog post which had some of these detection mechanisms in there as well. So yeah, like right now, all of the detection mechanisms for this are very fragile because they're all based on like the class names, on the namespace names. They're really fragile detection mechanisms. There really isn't a good way of inspecting the actual code running. And like to get so you have to rely on multiple IOCs in order to properly detect this kind of attack. So I hope that makes sense. And future work, really quickly, because I think I'm pretty much over all the time that we had. Job control. Right now, there really isn't a way of like managing jobs in the agent, so that has to be done. I'd like to see C2 profiles. I know I can do it because from the way I designed it, I just have to take the time to do it. More modules and comms. I actually have a Pastebin C2 listener, almost 70% done. I just have to hook it up client side. RESTful API for automating things. If you're familiar with Death Star, I want to port that over to SilentTrinity. So like you can just do the same thing that you did with Empire and SilentTrinity, which would be really cool. More languages. I like to see R and Ruby in here because why not give Ruby some love? Run modules and disposable app domains. That is my main focus right now. I'm 95% there. So unloading those assemblies after a module executes is sort of a big deal because like that would get rid of the current detection mechanism of looking through like the process after a module executes and seeing like all the evil assemblies, right? So that's sort of my main focus right now. Okay, now questions.
We got time for a few. Is MS-build the .exe that is communicating back and forth to the C2 server?
MS-build.exe. Yeah, I mean, so if you look at it through Process Explorer, yes, absolutely.
There was one here. Let's see. He hated you. There we go. He says he loves that he hates you right now, I think. What about orgs that do SSL MITM and run a sandbox on the line? Are you capable of encrypting the zip file and decrypting on pull?
Yeah, that's exactly what this new version does. So the new version has fully encrypted communication between the server and the client. So if you inspect the wire, you'll only see just blobs of data being transferred back and forth via HTTPS. You won't be able to see any of the actual stuff, because it's all encrypted using a public key exchange.
And then somebody wants to know what your Twitter handle is on. What your Twitter handle is.
There it is.
Okay. Let's see. And there was a lot of questions. I mean, the consensus from all the questions coming in is that this is amazing and really awesome, and you're blowing a lot of minds of like defense and defer guys and people, and they're trying to figure out how to do this. So, any final words or thoughts for today's webcast?
I would probably say to the defensive guys that don't worry, because we're going back to the cat and mouse game again because of the ANSI integration of the .NET. The problem with that is it's in 4.8. So unless Microsoft forcibly updates all of the .NET framework versions on Windows 10 machines to 4.8, I'm gonna probably guess like it'll be a problem like having .NET 4.8. But like you'd have to update your entire organization's .NET framework version, which it can be done probably. I don't know. That's the only thing. But at the end of the day, we're going back to the cat and mouse game. So this is basically the era of when PowerShell offensive tradecraft was discovered. In a couple of years, this is probably going to be shut down, at least partially.
All right, so this was a Black Hills Information Security webcast. If you need penetration testing or threat hunting or red teaming, don't forget us at Black Hills. And then this will be available on our YouTube channel, and we'll also put it on the blog. Marcelo, thank you so much for joining us today, and thank you all for listening.
Thank you. Have a good day.
All right. Bye, everybody.